Hello there, everyone. My name is Dylan Binu, and I'm going to be taking you through my analysis of the square submatrices algorithm. Let me share my screen really quickly. All right. Okay, so here it is. I'm going to be taking you through each step, so please bear with me. Initially, up here, we have a print matrix function, which prints every value within the matrix. Then we have a check matrix function, which checks each value, checks the matrix to see if there is a square submatrix in there that equals to the integer v that we pass to the function. We also have a test function, which tests to see if uh, it calls the check matrix function, which we will also see in the bottom here. So we're creating a vector of type vector, an integer vector, and we're calling it by matrix. And we're also creating an integer vector called P1. And you will notice that into the matrix, we push P1 3 times. So you have a dynamic vector of sorts. We have a nested loop here, which pushes into P1 within each matrix index, the different values that are in I. So you'll notice that within this nested loop. Okay, so we go down here, the print matrix function is called, and we're passing my matrix to it. And as you'll see, these were the values that were pushed into this function here, into the matrix here. So that's the output. Also here, you are also seeing the test function being called multiple times, and in comments, you'll see the output for each of them. If any of the sums of the subsquare matrices equal any of these values, you'll get a yup. If it doesn't, you'll get a nope. Down here is how the test function is coded. It'll call the check matrix function. If it returns true, then it executes yup. If it returns false, it executes nope. And we'll see how the check matrix function works in just a little bit. Here we have the print matrix function. Once again, a nested for loop. It goes through each value within my matrix and prints it out. Down here, I coded my own minimum of function because I couldn't find the time complexity of the min function that was originally provided. It's very simple, takes in two values and returns the smaller value of the two. Now here's the big function. We have check matrix. It takes the matrix and it takes an integer value. You'll see that it executes this print saying test 0, just to show that we've entered this function now. Then it'll assign the size of my matrix to x, and it'll assign the size of an element in my matrix to y. Then it would assign the smaller value between x and y to k. As you can see, calling the minimum function from up here, it also creates an integer sum variable, which will be used later. Now, as you can see here, I have a bunch of information over here, and this is just to help us visualize how this really large nested for loop works. It does look a little confusing, so let's go through it step by step. I just figured that it helps to use this to visualize it. So what is happening up here is current size is being set to 1. Then we go into the next one, and integer I is being set to 0. So before we get there, as we can see, x, because of this, is being set to 3, and y is being set to 4. And once again, here's the output of the matrix. So as you can see, x, there are three values here, and for y, there are 4. So that is the reason those are the values over there. For current size, it's being set to 1 over here, so it's 1. K is the minimum of x and y. So we have 3 and 4, so it's 3. Next, we go to the next for loop. I is set to 0 in this case. So let's change that. X minus current size is currently 3 minus 1. So that would be 2. J is set to 0 down here. Y minus current size is 4 minus 1. So that is 3. M is set to I here, and I is 0. So M is set to 0. I plus current size is 0 plus current size, which is 1, and N is also set to 0, and J plus current size is also, N is set to 0 because it's equal to J, and J plus current size is 0 plus 1, so that is 1. So you will understand this, these things here in just a little bit, but let's get started. So once you enter this innermost for loop, you will see that the value within my matrix Mn gets added to sum. So sum over here is set to 0. After J gets initialized to 0, within that for loop, sum gets set to 0, so it's currently 0. We look into my matrix Mn, and currently M is 0, N is 0, so that would be this value right here. If you recall, this is how the matrix is structured. So 0 and 0, this is the value. So the sum would be 0, 0. After that happens, N moves up by 1, increments. Then this is the condition, J plus current size. Since it is 1 and the condition says N less than J plus current size, this fails the condition. So it moves out to the outer loop, which is M. Then since it moved out, M goes up by 1. It then fails the condition in that loop, which is I plus current size. It's not, M is not less than that. So it moves up to the loop that is outside that, which is this one up here. And this is where the sum gets set to 0. So before the sum gets set to 0, after we move from this loop to this loop, and after we move out of this loop, you will notice here that there is an if condition. So you saw that we added to sum this value right here, which is 0. So after we do that, we check to see if the value within sum is equal to the value that is passed into the check matrix function. If it is, it'll return true. If it's not, then we will continue. We will continue going outside of even this loop. So next, we're at J is 0. So since we've moved out of this loop, J increments by 1. And it increments by 1, and it passes this condition because 1 is lesser than 3. So it goes in here again. Once it goes in here, M gets set to I, which is 0, gets set to 0, and then it passes this condition. So it goes into the next loop. And over here it gets set to 1 because J is equal to 1 and N is being set to J. J plus current size is now 1 plus 1 because J is 1 over here and current size, if you recall, is 1 right now. So it gets set to 2. And then yes, we then can perform this again. Sum is equal to my matrix Mn. So M in this case right now is 0, N is 1. So that would be 0 of the X index and 1 of the Y index. So that would be this value right here. After we do that, N increments by 1, 2, it fails the condition, goes out of the loop. M increments by 1, fails that condition, goes out of the loop again. Since it's gone out of these two loops, once again, this condition is checked. If sum is equal to V, it returns true. Otherwise, we continue with the algorithm. So it goes on over here, increments up to 2. So still passes this condition because 2 is still less than or equal to 3. Goes down here, M gets set to I again, and then goes within that loop. N gets set to 2 this time. J plus current size is 3 this time. So the check right now, my matrix Mn would be 0, 2. So 0th index of X, 2nd index of Y. So it is this value right here. After that is done, this increments by 3, goes out of that loop. this increments by 1, goes out of, this increments by 1 and goes up to 3, and then goes out of the loop because it fails condition. This increments by 1 and then goes out of the loop. And after that, the condition is performed. If it's true, it returns true. If not, it's false. And we're going to assume that it's false for the entire time so we can see the entire working of this. It goes up here, then this gets set to 3 now. So far, just to recap, we've checked this value, we've checked this value, we've checked this value, which all behave as independent submatrices, independent square submatrices. So J gets set to 3, and the condition here is J is less than or equal to Y minus current size. So Y minus current size is 3, so it passes the condition because J is lesser than or equal to Y minus current size. So goes into the loop, M gets set to 0 again, which is the value of I, goes in to the next loop, N gets set to 3. It remains at 3 because it's equal to J. And then J plus current size goes up to 4 this time. After it goes to 4, that we check the next value, which is Mn 0 and 3. So 0th index of X and the 3rd index of Y. I hope that makes sense. After we're done doing that, N increments again. This time it goes out of the loop because it obviously fails the condition. Once again, it's N less than J plus current size, then goes out of the loop once again. This increments, we go out of this loop. Now, J is incremented by 4. So now that it fails this condition, J finally increments a little bit too much and it fails this condition, and we finally come out of this loop and we go into this one, and I increments by 1, as is seen over here. It increments by 1. It still passes its own condition, which is X minus current size, I less than or equal to X minus current size. So it increments to 1, and then we move into the loop again. So J gets set to 0, as you can see down here. Y minus current size remains at 3. We go into the loop. M gets set to I, which is now 1. So it remains as it is. I plus current size now. If you recall, current size is 1. I is also 1 in this case. So I plus current size is 2. We then go into the next loop. N gets set to 0 because N gets set to J, which is 0. J plus current size right now is 0 plus 1, so it gets set to 1. Okay, so now we're in this check again. What are we adding to the sum? My matrix Mn, so that would be first index of X, 0th index of Y. First index of X, 0th index of Y. So that would be 1 right here. After it does that, this increments by 1, goes out of the loop, this increments by 1, fails the condition, goes out of the loop, this increments by 1, and it doesn't fail the condition, so we go back into the loop. So M gets set to 1 again, which is I. We go down again, N gets set to 1, so this increments. After this does, we are checking M1 and N1 right now. So that would be the first index of X and the first index of Y, so this value. So recap, we've checked this value, we've checked this value, we've checked this value, and now we've just checked this one and this one. So you kind of get the theme here. We're checking every single individual value here by doing this. So after we do that, we're same routine, N increments, fails the condition, goes out, M increments, fails the condition and goes out. Then we go back up here, it increments to 2, because we still have more indexes in Y to check. So it increments to 2, we go back in here, this gets set to 1 again, this gets set to 2, this gets set to 3, condition passes, we check X's index of 1 and Y's index of 2. So X's index of 1, Y's index of 2. So this one, now we check this one too. Comes out of the loop, same pattern, 3, this goes to 2, this goes to 3. J is 3, Y minus current size is 3. The condition is J less than or equal to Y minus current size, so it remains in the loop. This gets set to 1 again. This remains at 3. This increments to 4. We're checking X index 1, Y index 3. So we've successfully checked all of these values too now. Next, we're going to go even further. I'm going to speed up this process a little bit. So we go to 4 here. Then we go out of this loop because this condition fails now. So now this goes up to 2. So you'll notice x minus current size is also 2, but the condition is I less than or equal to x minus current size. So it passes the condition. So we go into the loop again. J gets set to 0. Y minus current size is going to remain at 3 because current size hasn't changed. M gets set to I, which is 2. I plus current size is going to be set to 3. N gets set to the value of J, which is 0. J plus current size is going to be 1 again. Okay, so now we're checking the second index of X and all the indexes of Y. So we're going to start with the 0th index. It's 2, increment by 1, increment by 1 again, go out here, increment this. This gets set to 2 again. This remains as it is. This gets incremented by 1. So 2 and 1, so second index of this and the first index of Y. So as you can see, that works out. This gets incremented to 2. This gets incremented to 3. Then this gets incremented to 2, passes the condition, goes through. M gets set to I, which is 2. N gets set to J, which is 2 as well. This gets incremented. J plus current size, 2 plus 1 is 3. So we're checking M2 and 2. So the second index of X, second index of Y. All right, so increment this. This now gets set to 3. Now we're at the final index of Y. So it's a final condition that needs to be checked. M gets set to 2 again. This remains at 3. Apologies. This gets set to 4. All right. So second index of X, third index of Y. Second index of X, third index of Y. So we've successfully checked every single value, individual value within the matrix now. So what do you do about the larger subsquares? So for that, we will see it work right now. So N gets set to 4, comes out of the loop. M gets set to 3, comes out of the loop. J gets set to 4, so it fails this condition over here. So that comes out of the loop. I gets set to 3, so it fails that condition too. So for the first time, we're coming out to this primary for loop. And over here, current size is now incrementing. So it increments from 1 to 2, which determines the size of the subsquare that we're searching the sum of. So far we've searched all the subsquares with a size of 1. We are now going to be searching for the subsquares with the size of 2. So squares that look like, oh, oops, that didn't work. Squares that look like this, squares that look like this. I'm sorry, I'm not really able to pinpoint it the right way, but I hope you get the idea. All right, so K remains at 3, current size is now incremented to 2. So then we go back into the loop. I gets set to 0. X minus current size now is 3 minus 2. So this gets set to 1. 1. J gets set to 0 again. As you can see here, we're just going through a loop structure again. Y minus current size is 4 minus 2, which gets set to 2. M now gets set to the value that is an I, which is 0. I plus current size is 0 plus 2, so that gets set to 2. N gets set to the value of J, which is 0. And J plus current size is also 0 plus 2, which is 2. So let's go back into this check here. All right, so we check the position Mn. When we do that, we're checking 0, 0. So 0th index of X, 0th index of Y. So we check that right there. Then next, we increment this by 1. After we do that, we do the same check. 0th index of X, first index of Y. So this one right here. So this is the reason I have these noted down this way. So we've checked 0th index of X and 0th index of Y. Now we check 0th index of X and first index of Y. Next, this increments to 2. Fails the condition, we come out of the loop. This now gets incremented to 1. So it goes back into the loop. This now gets set to J, which is 0. And J plus current size remains at 2. So next, we're checking the first index of X and the 0th index of Y right there. First index of X and 0th index of Y. So first and 0. And then this increments, and we search the first index of X and the first index of Y, as you can see. Once we're done doing that, this, whoops, sorry about that. This now increments to 2. This increments to 2. We come out of the loop. After we come out of this loop, we can see that the condition check is done here. If sum is equal to v, then if the sum of all of these, remember the sum now contains the values of all of these, all four of these now. It's not just a single value like it was before. If the sum is contained in that, then if it equals to v, then we return true. If not, we continue with our algorithm. So we're moving j up to 1 now. After we do that, we go back into the loop. M gets set to 0. N gets set to 1 now because it's setting to j. Then j plus current size would be 1 plus 2 now. So that gets set to 3. So now we're in a completely new situation. So these values are all going to get replaced. 0th index of x, first index of y. 0th index of x, first index of y, right there. So we start off there, then this increments to 2, 0th index of x, second index of y, we increment to 3, fails the condition, this goes up, we increment that to 1, go back in here and get set to 1 again. So next we're checking 1 and 1, next this goes up to 2, next we're checking 1 and 2, and next this increments to 3, this increments to 2, and we come out of the loop. So I'm sorry, this extra one should not have been here. We are looking at these 4 ones now. 0, 2, 1, oops, I think I made a mistake here. It's supposed to be checking these values. So 0, 2, 0, 3, 3, then 1, 2. Actually, I apologize. I don't think it's that. It is 0, 1. Sorry about this. 0 and 1, 0 and 2, then 1 and 1. It's 1 and 1, and then 1 and 2. That makes most sense. This right here. I'm sorry about that confusion, but I hope that is cleared. We're checking the next square now. After this, these all get reset again. But yeah, hope you get the idea. I'm going to clear these just so it's easier to explain. Okay, so after we come out of this loop, the sum is being checked over here. Then we go out over here. J gets incremented. It passes this condition since the j less than or equal to y minus current size. M gets set to 0 because I is 0. N gets set to the value of j, which is 2. J plus current size is 2 plus 2 now, which is 4. So now we check 0, 2. Then this gets incremented. We then check 0, 3. Then this goes up to 4. We come out. We increment this to 1. Then this gets set to 2 again. Then next we check 1, 2. This increments, and we check 1, 3. So as you can see, we're checking 0, 2, 0th index, 2, this one right here, then 0, 3, then 1, 2, then 1, 3. So we're checking this square right here. So we check this square, we check this square, and we check this square. After we do that, obviously it increments, this increments, fails conditions, and goes out, and then the check is done to see if that subsquare equals, if the sum of that subsquare equals v. Next, we go back up here. Now that we've reached the end of the y-index, j goes up to 3, and we break out of the loop again. So we break out of this one, I then gets incremented to 1 now. So it passes the condition because I is equal to x minus current size currently, because 1 is equal to 1. Condition is I less than or equal to x minus current size. So goes into the loop, j is equal to 3. Sorry, j right now it gets set to 0 again. Y minus current size is, it is still 2 because it's 4 minus 2. Nothing changes there. M gets set to I, which is 1 right now because it just got updated. I plus current size is 1 plus 2, which is 3. N gets set to the value of j, which is 0. j plus current size is 0 plus current size, which is 2. All right, so we're moving down the x index now. So, or the x-axis, if you want to view it that way. So M1, N0, so we're checking M1, N0. That is, we're checking 1, 0. This gets incremented. We're checking 1, 1. This gets incremented, break out of the loop, go up here, increment this. This gets set to j, which is 0. This gets set to, it remains at 2, I believe. J plus current size 2, yep. So we then do 2, 0. Then we do 2, 1. 2, 1. All right. You notice we're doing these four now. So 1, 0, x index of 1, 0th index of y, 1, 0, 1, 1, 2, 0, 2, 1. So we move the square down now. We initially checked all these four squares up here, or these three squares up here rather, and now we're checking these three squares down here. So same logic, this increments, we break out of the loop. Now that we have that complete square, it checks to see if that sum equals v. Next, we break out of this loop again. J increments by 1, goes back into the loop. This gets set to 1 because that is what I is. N gets set to j, which is 1. And then j plus current size now is 1 plus 2. So that is 3. So we're checking 1, 1, where it increments. We check 1, 2. It increments again, fails condition. Then it goes up here, increments this, goes back in here. This gets set back to 1. So 2, 1. And then this increments, and we check 2, 2. So 1, 1, 1, 2, 2, 1, 2, 2. So 1, 1, 1, 2, 2, 1, 2, 2. Yep, that's right. So we check this square just now. This increments. We go out of that loop. That sum check is done. We go back out here, increment this. We go back into this loop because it still fulfills this condition up here. So this gets set to I again, which is 1. This gets set to j, which is 2. Then j is 2 right now, so 2 plus 2 is 4. We check 1, 2 right now. Then this increments. We then check 1, 3. It increments. We break out of the loop. We go up here, increment this by 1. Go back down here, set this to j again. Then we check 2, 2, as you can see. 2, 2. This increments again. And we check 2, 3. All of these. 1, 2, 1, 3, 2, 2, 2, 3. 1, 2, 1, 3, 2, 2, 2, 3. We've checked this final square now. So now that we've checked this final square and reached the final y index, we go up here, this increments. We go up here, this increments. Now, and then obviously we do the sum check. Then now that we come out of this, j increments again, and it fails its condition because we've gone through all the y indexes. I increments as well. Now that we've gone through the entire matrix, it increments again, and we go back out. We've gone through the entire matrix, checking the submatrix squares with a size of 2. So we go back out here and then increment current size to 3. So now that we do this, you can see that this will be the final iteration of this loop because the condition says current size less than or equal to k, and we are at the value of k now. So this will be the final time. We are once again going into the loop. I get set to 0. X minus current size is now 3 minus 3, which is 0. J gets set to 0. Y minus current size is 4 minus 3, which is 1. M gets set to the value of I, which is 0. I plus current size is 0 plus 3, so it remains as 3 over there. N gets set to 0 because J is 0, and J plus current size is 3 right now. All right, same logic. Now you'll see how all of these, oh, whoops, sorry about that. How all of these are now implemented. All right, so this becomes 0, this becomes 0. We're checking 0 and 0. That is valid, this increments. We're checking 0 and 1. This increments again. We check 0 and 2. This goes up to 3, fails the condition, goes up here, this increments. We go back down here, this gets set to 0 again. So now we're checking 1 and 0. Next, we're checking 1 and 1. Next, we're checking 1 and 2. Same logic, 3 goes up here, this increments, goes down here. This gets set to 0 again. We're checking 2, 0. And as you can predict, same logic, 2, 1 and 2, 2. This should be 1, 0. All right, so if you notice, you're checking every single value that is in this 3 size square submatrix. I wish I could annotate it, but I hope you see that. These 3 here, you're checking to see if this sum is equal to this value. And you'll see that right here. Obviously, once these increment accordingly, because I kind of just went through all of these, but then this will increment to 3. This will increment to 3. We break out of the loop. That check is done. Then j increments by 1. We go back in. This gets set to 0 again because that's the value of I. This gets set to, this remains at 3. I'm sorry, this gets set to 1 again because it's getting set to j. J is 1, current size is 3, so this increments to 4. All right, we're moving towards the right now. So 0, 1, that would be, yep, that would be this one, 0, 1. So you can already see that we're going to be checking this. So I'm just going to go through this really quickly because it follows the same logic. Then this becomes 0, 2. And this becomes 0, 3. This becomes 1, 1. This becomes 1, 2. This becomes 1, 3. This one's 2, 1, 2, 2, and 2, 3. I hope you followed that. That's just what is being done here. So we have now checked this subsquare. Now, this is the final subsquare that you can check. At this point, this would be at 4. This would be at 3. You'd break out of here. You would then check this to see if it's equal to V, if the sum of that subsquare is equal to V. Then you would go back out. This would increment to 2. This would increment to 1. As you can see, that condition fails. Then this would increment to 4. And we are now officially out of the entire nested for loop structure. Now, if the value V wasn't found in any of those submatrix sums, then we would officially be out of that loop and we'd return false. So yes, that is the logic behind that. Pardon me for a second. All right, I apologize for that. Oops. Let's just do that. Okay, I hope you can hear me now. All right, so we're going to go through, now that we understand how this works, let's go through some loop invariants just to check the correctness of this. So for the outermost loop, we're fulfilling this condition. So k, which is the minimum value of x and y, will always be less than or equal to y, or it will always be less than or equal to x. So it's kind of self-explanatory, and this is maintained throughout the initialization, the maintenance, and the termination of the entire loop. Over here, the condition is x will be greater than or equal to current size, or y will be greater than or equal to current size. And the same goes for this one here, for the next loop. That is maintained too when we get in here. M will always be less than or equal to the size of my matrix. And when we go to the next loop, N will always be less than or equal to the size of an element in my matrix. So those are my loop invariants. And if you notice how the code iterates, you would notice that those conditions should always be true, hence proving that this algorithm indeed works. Now I'd like to go through the time and space complexities really quickly. The space complexity, first, we have these over here. So these are all order of 1 because we're declaring functions. The vectors, they're order of n. The for loops, once again, order of 1 space complexity because nothing really is being done in there of significance. The function here is also order of 1. These are all order of 1 as well, space complexity. This function is order of 1, and these are all order of 1 too. So you'll notice here the total space complexity, order of 1 occurs 20 times, and order of n occurs 2 times, and I believe that is up here, and there are the vectors, and since one vector goes into the other vector that many number of times, it's order of n squared. So you put that in here, you simplify it. Order of 1, the constant time complexity can be ignored. So order of n squared, and that is the final space complexity, is order of n squared. So let me just remove that. Now, the worst case for this would be if you take the largest integer value possible and you use that for each vector. I could be wrong on this. This was just my assumption. So when you do that, the calculation would be the order of that value versus the order of the same value because you're putting that vector into the same vector, and it would be order of this number squared, which would be really high. However, when x and y are equal to 1, when you only have one value in there, that would be the best case because the size of the matrix would be 1 by 1. So n would be 1, and in this case, when you put it into the equation, you get order of 1. So because order of n squared is order of 1 squared in this case, so it's order of 1. Now, when it comes to the time complexity, you'll notice that once again, functions are all order of 1. For a nested for loop, it's order of n squared because nothing significant is done in there, but we still iterate through it a number of times, n times, n squared times. Down here, order of 1 for this function again. Once again, another nested for loop, which is why this function is order of n squared in time complexity. This is order of 1, the min function, and the check matrix. Because of this 5-layered nested for loop, it's got order of n to the power of 5. So that is the calculation for this. Order of 1 occurs this many times, then you've got an order of n squared nested for loop. You got another nested for loop, then you got a 5-layer nested for loop. And when you simplify all of that, you ignore the constant big O, and you get a total of order of n to the power of 9. Now, the worst case, once again, in this situation would also be when you take a vector size that is the maximum possible size that it can be. And once you do that and you put it in there and it gets raised to the power of 9, that would be a really large scenario. So that's the calculation for that right there. I just plugged it into the equation. The best case, once again, is when the vector size is 1 or the matrix size is 1 by 1, 1 or 1 times 1, however you call it. This is the calculation for that as we plugged it into the equation, and that is the result, order of 1. So that, I believe, completes every requirement for this assignment. And I do realize that I didn't improve on the time complexity, but as for now, I was only able to analyze it. So I hope that was helpful, and yes, thank you for listening.